So suppose I have this second order differential equation. This is a homogeneous, autonomous second order differential equation. It's homogeneous because it does not have a function depending on any other variable. In our case, say t, and autonomous because all the coefficients here are constants. They're all 1. So how would you solve this? Now, there are many direct ways to do this, but here we want to show that we can transform this into a system and treat it like a couple of first-order equations. To do that, I'm going to introduce 2 new variables. x1 equal to y and x2 equal to y prime. Then x1 prime is y prime and x2 prime is y double prime. Now what I'm going to do is I'm going to substitute a couple of these into our equation right here. So first I'm going to rewrite this as y double prime is equal to negative y prime minus y. Now I'm going to substitute x2 prime for y double prime here, x2 for y prime here, and x1 for y here. Then I will get x2 prime is equal to negative x2 minus x1. Note also that x1 prime equaling to y prime and x2 equaling to y prime are the same. So we can write this as x1 prime is equal to x2. So if I write both of these in matrix notation, it becomes x1 prime, x2 prime is equal to 0, 1, negative 1 times x1 and x2. If you write these in scalar form, perform row operations on it, they should turn out to be like these. Now let's say that we will regard this vector as x prime, this matrix as A, so 2 by 2, and this vector as x. Then, in a shortened form, this notation becomes x prime is equal to A times x. Now this is something we can solve using eigenvalues and eigenvectors. Remember we introduced 2 new variables, x1 and x2. So that means when we solve this thing, we should get 2 solutions. Keep this rule in mind, and that if x1 of t and x2 of t are 2 solutions, then by the principle of superposition, b1 x1 of t plus b2 x2 of t is also a solution where b1 and b2 are arbitrary constants. So the solution of a system that looks like this looks like this plus b2 x2 of t. And this is our all-important line right here. Now, if you take the Vronsky determinant, now if you don't know what the Vronsky determinant is, I made a video on that, and it's basically taking the determinant of the two solutions here and seeing if these two solutions form a fundamental set. So if you take the Vronsky determinant of these two, and it turns out not to be equal to 0, then we have fundamental solutions. We're good. Just recall that t here is our independent variable. So let's solve. Let's solve these. We will make a kind of a big assumption here for the form of our solution, which is we will assume that our solution, this, has this form. Where this is a scalar and is actually the eigenvalue, and this is a constant vector and the eigenvector. So you can prove that these are in fact the eigenvalues and eigenvectors by substituting this form of the solution into this. If you do that, you will actually end up with a minus lambda I v is equal to 0, which we have seen in my last video is how you solve for eigenvalues and eigenvectors. So if you're going to solve this, so either this v can equal to 0, which is what we call the trivial solution, or all of this can equal to 0, which we call the non-trivial solution. We are always more interested in a non-trivial solution. So let's go with that. Now I want you to recall the method of solving the eigenvalues and eigenvectors, which is you find the eigenvalues by finding the determinant of a minus lambda I and equating it to 0, or you can use this equation, which is simply what you will get by doing that. And then individually, you will find the eigenvector, by putting in the eigenvalues into a minus lambda I v is equal to 0. Let's see this whole business with an example. Now suppose you have a as 2, 0, 0, 3 times x. Now we said we will assume x is equal to v times e to the power lambda t. This leads to a minus lambda I times v is equal to 0. We've seen that all before. So if I perform this on this A, I get 2003 minus lambda 00 lambda equal to 2 minus lambda 0 0 3 minus lambda. Now to find the eigenvalues, I'm going to use this equation. So the trace of A is 2 plus 3, which is 5, and the determinant of A is 6 minus 0, which is 6. So it becomes lambda squared minus 5 lambda plus 6 is equal to 0. And if you solve this quadratic equation, you will get lambda is equal to 3 and 2. And we have our eigenvalues. For our eigenvectors, we will deal with these individually. So for the first one, I'm going to do this operation by substituting lambda is equal to 3. So I have 2 minus 3, 0, 0, 3 minus 3, which is minus 1, 0, 0, 0. And they are all multiplied by the eigenvector v. And this is equal to 0. So performing row operations, on the first row, you get negative v1 plus 0 v2 is equal to 0. So this basically tells us that v1 is equal to 0. And so since we don't have any way to find a v2, we just can see from here that it is pretty much anything. v2 can be anything. It has no limitation or restriction. So we don't want to assume v2 to be 0 because that will give us a trivial solution. So we'll just let it be 1. So our first eigenvector is 0, 1. We'll do the same exact thing for the second one. So we will put our value of lambda over here, times it by v. So we have 2 minus 2, 0, 0, 3 minus 2 times v1, v2 is equal to 0, which is 0, 0, 0, 1, v1, v2 is equal to 0. Now performing row operations on the second row, we get 0 v1 plus v2 is equal to 0. From here we can see that v2 is equal to 0, and v1 over here can be anything, has no restriction on it. And this time we'll let v1 be 1. So our second eigenvector becomes 1, 0. Now, the penultimate step. We have our two eigenvalues, and we have our two eigenvectors. We're going to put them together. We assumed our solution to be of the form this. So our first solution is e to the power first eigenvalue, which is 3t, times the eigenvector, which we said as 0, 1. Our second solution is e to the second eigenvalue, which we said is 2t times 1, 0, which is our second eigenvector. Now all the way up above, we said that our solution should be of this form. So the solution becomes b1 e3t 0, 1 plus b2 e2t 1, 0, where this is x1 and this is x2. So it's the same as b1 x1 of t plus b2 x2 of t, which we said is the form of the general solution.